Welcome everybody to this afternoon's talk to be given by Dr. Tiantian Liu. Dr. Liu, she's currently working at the museum. I would say that it should be a Museum of Natural History in Berlin. But before then, she did her undergrad at the China University of Geosciences in Beijing. And then she went to Beijing University to work for her master degrees. And then after that, she went to Germany and did her PhD research at the Technical University of Berlin under Dr. Greg Michael, and then Professor Jürgen Oberst of FDLR. Now she's now working at the as I said earlier, at the Museum of Natural History in Berlin, and her specialty research specialty is on impact on the formation of crater and ejecta. As you will hear from her immediately about the formation of lunar megaregolith and the evolutionary history. Yeah, Dr. Liu, please start your talk. Thank you so much.
Okay, thanks very much for invitations. Today I will talk about the consequence of cumulative impact mixing on the moon. As you know, the moon has experienced a very long time bombardment since its formation. We can still see some evidence on the present day. As you can see from this background image, a great number of these crater structures. For the formation of each impact event, it is accompanied by the variation of the material compositions over its surrounding regions. From this schematic, you can see some of target material is excavated. These materials, we call it ejecta. This material will be transported to the regions further away. Not only this ejecta, the materials underneath crater floor will also be affected. Based on the observations, you can see from this right image, this is the formation of very young impact events on the moon. You can see the formation, after the formation of this impact crater, we see some dark areas over this surrounding this impact crater. This is excavated materials caused by these impact cratering events. It changed the material compositions near the crater regions. You can also notice this rays here. It suggests that there are also a small amount of materials that can be transferred to the regions even further away. So this is the consequence of one single impact event. What if there are subsequent impact cratering events occurring over the regions that has already been affected by these impact events? This is what we are going to talk about today, the cumulative impact mixing. For your better understanding, I show you a simplified schematic so you will understand the general consequence and how important the cumulative impact mixing affect the material composition. Assuming here there are surface with component X and the component Y, at the very beginning, there are impact events occurring on the surface of component X. Some X material transported to the regions of component Y. Then there are impact events on the surface of component Y. The excavated component Y covered on the previously transported ESC material. As you can imagine, with the time going by, the material compositions will become more and more complicated. If we assume that these different colors represent materials of different components, what we can see, it will be similar like these variations here, become more and more colorful. And then at the very end, what we will get, it will be a piece of materials consisting of chaotic components and very, very complicated. So this is a major big picture of the consequence of cumulative long-term impact mixing. I keep talking about the components and the compositions. What this exactly mean? It can be anything that we are interested in. For example, it can be the products of impact cratering process itself, like a very important component of impact melt. It can also be the volcanic materials like Mari and non-Mari materials. And it can even be the size of the fragmented material. So these components can be anything that we are interested in. So now the question is why it is necessary to understand how the impact cratering and cumulative impact cratering affect these different components, how affect their spatial and abundance distribution. Because we later know that based on, if we understand better about their evolution history, we can use this component to better understand what happened in the past. For example, if we understand the diffusion of impact melt, we can constrain the bombardment history. For the Mari diffusions, we are able to constrain the volcanic history. And for the fragment size, by understanding how the size evolves with the time, and we can understand the evolution of crust. For more details like the megaregolith evolution and also the regolith growth history. Today, I will only show you these three components, and due to the time limit, I will say more in details for the first part of impact melt, and for the other two, I will keep it more briefly. Of course, now first the bombardment. Okay, the bombardment. As you know that when the moon was just formed, it has experienced way much more intensive bombardment than what we see on the present day. For the timeline of this early bombardment and how the impact rate evolved with time, it is still a topic that has been debated. Typically shown in this histogram, this plot, there are three types of models. The very typical one is tail end, accretion tail end model. This red color. In this model, it suggests the impact rate gradually decrease with time. And another extreme case is this blue curve, the terminal cataclysm. In this model, it suggests there is a very, very high impact rate at a certain time period, around 3.9 gigayears. This proposal mainly derived from the analysis of Apollo samples. After returns of Apollo samples, people find a lot of impact with age of 3.9, and then it proposed that there has a very high impact rate at this period. And then another one, the yellow-green one, the sawtooth one, it considered the tail end and the terminal cataclysm as two end members, and the impact rate has something in between. So this is what we can do if we what we can learn from the impact mixing model to whether we can use this model to at least identify which one is more comparable with the observations. To understand the bombardment history, the moon is the best body because there is no water, wind, atmosphere, and the structure has been very well preserved. And more importantly, we have a lot of samples, Apollo missions, lunar missions, and the Chang'e 5 mission. These samples provide us ground truth reference for constraints of bombardment history. However, it has been found not as easy as what people expected. The main reason is that it is very, very difficult to understand the arranging of the different components contained in the lunar samples. Assuming this is a piece of samples collected from the Apollo 16 sampling size, you also notice in the background here is huge, large impact basins, Imbrium and Serenitetics. So the question now is, what the relationship of this piece of materials with these two joint basins? How much materials derived from these two basins? This is a not easy question to understand, but if we think about these questions in the other way around, we record the consequence of each impact event since its formation, and then this question will become more easier to address. This is what we are talking about today, the Monte Carlo impact mixing model. With this model, we are able to trace the source of different components. And then with these models, we are able to constrain the fractions of different components in the collected samples. And more importantly, with this modeling result, we can also estimate the compositions of materials over the regions that has not been ever sampled. This will be very helpful for the future sampling mission. So how this model works? For this Monte Carlo model, the very first important thing to get is the list of impact cratering events. So for this list, the two most important thing is the age of these impact cratering events and also the size of these impact events. With this list, we can then simulate the impact events one by one. Of course, we start from the oldest impact events. We'll record and simulate its excavations and ejected deposition process. After the formation of this impact event, this model will record everything that changed by these impact events. And then the second old impact events happens, and the model will do the similar things, record all the things changed by these impact cratering events. After the formation of the youngest impact events, now the model can give us the material composition on the present day. Of course, for the key process, like excavation and ejected depositions, we need many scaling laws, parameterization methods to do that, but I will not go in deep for this part. As I mentioned, for the impact events, especially for the very late period, the excavations, the occurrence of each impact event will change the material compositions in a more complicated way. For example, here is a late surface with three age of materials, and then the impact events will excavate the three types of materials and then generate a new layers on the top. Of course, it will also contain new materials directly come from the young impact event itself. For these Monte Carlo models, it can not only record the material compositions in special dimensions like over the surface and with the depths, but also the material compositions, abundance of different components over the surface and at different depths. This is the framework of the model. Of course, looks very simple, but if we really want to use these models to investigate anything we want, we need to further improve these models based on the things we want. Then the impact melt, as I mentioned, impact melt is the product of the hypervelocity impact cratering process. This hypervelocity impact cratering process generates great amount of energy, heat, generate very high temperature. So the target materials, some of this will be heated and then melted. The very important thing to understand here, to remind here, is that the isotopic time clock of this melted material is reset due to this high temperature. To say this a simple way, that the impact melt, by estimate the age of impact melt, we can estimate the formation time of impact cratering events. So if we have the distribution of differently aged impact melt, and then we can use these distributions to put into this the plots on the right to constrain the bombardment history during the early period. As an example, this is based on these models. This cartoon shows you the distributions of serenitatis melt. Where is serenitatis melt is in between the Imbrian and the Crisian. In these cartoons, you can see that since the formation of serenitatic basins, it generated a lot of impact melt. And this impact melt mainly distributed near the basins, as you can see in this redder color. And you can also see some materials, generated melt materials transported further away, but the abundance is quite small, as indicated by this blue and gray color. This is an example of this serenitatis melt and how it evolved with time. And in this model, for each of impact events, the model will do the same thing. So after the model finished, and we can have not only the average distributions of the surface at greater depths, at different depths, but also we see great special variations, and different small regions, they will show different melt compositions. And first, the average compositions. Mentioning the average compositions, the first thing occurs in my mind is meteorites, because lunar meteorites represent locations randomly distributed over the surface. So by analyze the melt distribution in meteorites, we can have comparable melt distributions with the predicted melt compositions from the model. In this histogram shows you the potential argon ages of these meteorites. You can see the 3 general peak at 3.8, 4.2, and 4.4 gigayears. And then what we get from the model, in the plot below, you can see the model predicted results. The different color suggests the different input of impact flux. Like the red ones on the upper right plot, you can see it is related to the tail end models. The blue one, the terminal cataclysm, the very sharp peaks here, and the yellow ones represent the sawtooth models. So I input these different impact flux into my models, and then result in the different surface average compositions over the surface. And then compare with meteorites, the actual data that we got. And then we can see at least the terminal cataclysm, the blue curves, it shows only one sharp peak here. This is obviously not consistent with the meteorites. So, but for the other two, tail end and sawtooth, both has a comparable pictures of these melt compositions. And then from this modeling result, we can at least say that the cataclysm is very least likely is very least likely for the early bombardment impact rate. But the both tail end and sawtooth both are very comparable with the actual data contained in the lunar meteorites. So to further distinguish between tail end and the sawtooth, we need now the regional material compositions. As I mentioned that on the present day, the material melt composition shows very significant spatial variations. It suggests that for different small areas, they have different melt compositions. So what we now do is to estimate the regional melt compositions. Here we choose the Apollo sampling size because we have samples. Of course, this is most clever way to do. And then as what I showed for the meteorites, the upper plot histogram shows you the age of these samples. We can still see the 3 peaks, but for the model predicted result, the plot below, you can see now not only the cataclysm models, but also the sawtooth, both shows only one sharp peaks at between 3.8 and 3.9 gigayears. Only the models with tail end shows additional two significant peaks. So this result suggests that at least with the data that we have now from the samples, the actual data support more the tail end over the sawtooth and the cataclysm. So with this model, by understanding the evolution of melt materials, we now able to help interpretations of lunar samples. We now know that the majority of 3.8 gigayears melt in the return samples is derived from the in-brain ejecta. And of course, in addition to the in-brain contributions, the other contributions will also be can also be estimated. Another thing is about how to use the melt distributions to constrain the early bombardment history. Our model suggests that at least if the actual data we have now is representative, and then the model support tail end over the terminal cataclysm and the sawtooth. This is an example about how do we use the evolution of melt distribution to constrain the bombardment history. Now we move to the volcanic materials. This volcanic materials is important because in the return lunar samples, here in this image, you can see a lot of sampling sites located over the Mare surface. These dark regions. However, after the analysis of these samples, people found that in these samples, it contains not only Mare regions, but also Mare materials, but also a lot of non-Maria materials. And for example, for the Apollo 50 and 70, it ranged around 20 to 80%. Apollo 12 ranged around 30 to 60%. Although the others has smaller values, but still contain around 20%. So people becomes wondering, where does this non-marine material come from? Because all these samples directly collect from the marine surface. So by understanding how the non-marine materials, marine and non-marine materials evolve with time, regarding the impact, cumulative impact mixing, we are able to address this question. As I mentioned, for each research goal, we need to further improve the model. For this one, the important thing is to simulate the Maria flooding. And now the target become divided into two parts, the highlands part and the Maria regions. And then the impact events can happen both on the highlands and the Maria regions. And the impact event will, some non-Maria materials will vertically excavate some materials and deposit on the surface. And then you can also see that some of these non-Maria materials, these gray color materials, transported from the surrounding highlands regions. We call these laterally transported non-Maria materials. Then a subsequent volcanic event happens. It will erase all the previously happened things, and then previously excavated and transported non-Maria materials, these gray materials, will be covered here. And then subsequently, with the formation of the subsequent cratering events, the material composition become more complicated because not only the differently aged the Maria materials, but also the materials previously buried by the volcanic events can also be re-excavated onto the surface. Then another two key parameters is first the volcanic flux, how the volcanic, how intensive at the past time and on the present day. In these simulations, we assume that impact cratering, Maria flooding start since the formation of the basins and will stop until the flooding of the major Maria regions. Another key thing is how much Maria materials is flooded, how much material has been filled in these areas. So this is based on the previously estimate. And then with this improvement, we can now estimate the abundance of non-Maria materials over the Maria surface. This plot shows you here the non-Maria materials vertically transported to the surface. Vertically means excavated underlying the Maria regions. The red color indicates the higher abundance. And then here in this plot shows you the materials, non-Maria materials that come from the surrounding regions, surrounding highlands regions. And it here called the laterally transported non-Maria materials. You can see these non-Maria materials mainly distributed over the Maria highland boundary. If we sum up both components, what we can get? We can get the non-Maria components on the present day over the Maria regions. And you can see very significant special variations over the Maria regions. For example, you can see some regions can have non-Maria mixture about over 80%. And then some regions, they can even smaller than 10%. For example, these porcelain regions, especially inside these regions, the mixture of the non-Maria materials is quite low. And then for these regions, nectarial regions, it has very old, so it is a very old surface, can have a mixture of non-marine materials about 30 to 50%. Now we can compare the predicted result with the observations in the samples. And then in this table, you can compare that for this Apollo 11, Lunar 60, and the Lunar 24, the predicted result and are comparable with observations. So what this mean? It means for these three samples, for the three sampling size, the non-marine materials contained in these samples many are the average contributions from the long-term lateral and vertical mixing, as what I showed you in the model. And for the other three, you can see very significant difference in between. And then it suggests that there must be some other process that plays a more important roles on the mixture of non-marine materials. After the observations of this geologic context, we found that for the Apollo 12, the Copernicus craters, this craters is very important. It may excavate a lot of non-marine materials underneath and transport these non-marine materials to the Apollo 12 sampling size. And for the Apollo 15 and 17, because it is quite close to the nearby massive, very steep, massive zones. So slumping of these massive materials can significantly mixed into this sampling size. So after the understanding of how the marine and non-marine materials evolved with the cumulative impact mixing, we are able to estimate and the mechanism of the origin of marine and non-marine materials. We see very significant spatial variations. We can compare between the vertical and the lateral transport, which play a more important on this on the mixture of non-marine materials. And we also estimate that we found that almost all the marine regions, it contains at least some non-marine materials. And in the top 5 meters, it can at least have about 10%. Now, very briefly goes to the third part about the size of fragments, how to use the mechanical process of cumulative impact mixing to understand the evolutions of fragment size and to understand the megaregolith evolution. The megaregolith, because of large number of impact cratering events during the early period, the lunar crust was significantly shattered and fractured, result in, on the present day, the very globally fragmented layer. We call this the megaregolith layer. The structure and how this megaregolith evolve is very important. Because based on this, we are able to, because it affects the understanding of lunar thermal evolution history and also affect our estimate of overall composition of the moon. For example, in this plot shows you the relationship between the heat flow and the bulk moon uranium abundance. These three curves represent the different input of megaregolith thickness. You can see that if different megaregoliths were taken, they will result in different estimate of uranium abundance. Of course, I don't know how this model works, but at least this plot shows us that the estimate of the constraints of megaregoliths plays a significant role on the estimate of lunar compositions. And then another key thing is the size of fragments. why we care about the size of fragments, because the rocks in the samples, the megaregolith, the fragments in the megaregolith is the main source of this the rock samples. And then this fragment size, these fragments in the megaregolith is also helpful interpretations of remote sensing data. And this bright ray craters shows here the figure on the left hand side. This bright crater result from the excavations of large boulders and fragments distributed near the crater and inside the crater. And on the right part, you can see that there are significant difference between the north part and the south part. At least for the south part, this has more dense bright ray craters compared with the south part has more bright ray craters compared with the north part. So we can so why it looks like that? Where does this significant difference comes from? So we need to understand how the megaregolith evolved and how the megaregolith fragment size distributed. But there are a lot of studies, they estimate the regolith thickness, but it shows us that there are huge difference ranging from about in thickness, it ranges about 0 meters to 0 even tens of kilometers. And for the fragment size in megaregolith, I don't see any previous publications that has such kind of constraints. So with this model, we can do both. We'll simulate the evolutions of megaregolith thickness, spectral variations, but also more importantly, the size of fragments in the megaregolith layer. Of course, we need to do the improvement of the models. The key thing is to simulate the fragment size distributions, both in ejecta and underlying the crater floor. We used a lot of previously works, and then for these details, I will not go to further go in further. But the key thing need to know is that with the formation of, after the formation of the one single impact event, it generates a huge amount of fragments. What if there is a subsequent impact events occurs on the previously generated fragments? How can we simulate this kind of consequence? And then the previous study told us that it has no significant influence on the statistical fragment size distributions, but it will also, the size of fragments still follow the power law, like here, but it will have a different slope. The different slope suggests that there will be, if the impact events occurs on the previously generated fragments, the fragment size, there will be way much more fragments with small size compared with the impact events occurs on a pristine crust. And then the maximum broken size in these ejected fragments, it also related to the size of these previously generated fragments. For the fragments below the crater floor, of course, it also has significant difference. But the major things need to know is that the small fragments, previously generated small fragments, they will become more and more difficult to be further broken. All these consequences will be considered in this model, of course. And then with this improvement, what we got, this is the simulation result with the improved the model. And then you can see in these animations, I introduce a volume weighted fragment size. LV. What this LV mean? It means you can take this in a very simple ways. The larger size, the larger values, the greater value LV, like suggests the more significant contributions from the large fragments, and the smaller values indicate the major roles of small fragments. So in this plot, what we can learn here, like for example, the blue color, 1 meter of LV, it suggests that in the top 2 kilometers, the majority of the fragments consist of fragments of meter scale. And for the blue regions, it suggests the majority of the fragments in the top 2 kilometers, it has a kilometer scale. Then with this simulation, we can do the global average corresponding to the different time period. And then as you can see, there are layer structures, and this, especially for the top 2 to 3 kilometers, the fragment size is gradually decreasing with time going by. But an interesting thing to note is that here is kind of opposite trend at 3.8 gigayears. This is a result from the formation of very young Orientala and Imbrium basins. These 2 basins are very big, so they are able to excavate very greatly, less fragmented fragments, less damaged materials from very great depths. So it will excavate and generate large fragments, and these large fragments will deposit on the surface. So this will result in this opposite trend. And you can see these layer structures, and then in the depth greater to about 10 kilometers, there is a very slight variations with time, but the major difference result in the top 2 to 3 kilometers. We always call these top layers as upper megaregolith, and the lower one is lower megaregolith. As I mentioned, the size of fragments is important to know. So I show you here for the different layer, different depths. I show you how much material, how much fragments has a scales of kilometer or meters or in meter scales. You can see obvious difference between, for example, the very top layers and the layer on in the greater depths. For the layers on the top, you can see the majority of fragments has meter scales, and for the lower, very lower layers, greater than 10 kilometers, the fragments in kilometer scales has primary contributions. This kilometer fracture, these kilometers fragments mainly contribute from the fracturing of the rock material instead of the separated ejected fragments. And in for the top one, there are a lot of fragments in meter scales. These meter scales mainly derive from the fragments transported in the ejector materials. Here is between 2 kilometers and 10 kilometers. Here we see a transition zones in between, and excluding the kilometer scales fragments, all the other fragments in different scales, they have comparable fraction. So now we go back to this figure. As I mentioned, in this figure, from the radar observations, this part, the upper part shows us that there are more abundant bright red craters. It means more craters that can excavate fragments, and the lower part has less craters that can excavate fragments materials. So what we can learn from this and from our models, why the upper part become more easier to excavate fragments compared with the lower part. From this plot, from our models, we see that in this plot, it shows you the thickness of very fragmented materials. You can consider this plot as the thickness of upper megaregolith. And then you can see a similar difference between the upper and the lower part at the degree of -4T8. And then in this plot, you can see the upper part has thinner fragment layer compared with the lower part. So it suggests that the upper part thinner, so it becomes easier to excavate fragments, and then it's easier to generate the bright red crater compared with the lower part. Here then, so with this impact cratering simulations of cumulative impact cratering, we understand how the megaregolith evolved and what the thickness and what the structure. And then with more important and interesting thing is that we find that the pivotal roles is derived from the basin forming events, especially the South Pole Aitken Basin. Okay, to have to summarize, I show you here today is about the consequence of cumulative impact mixing. How do I simulate this process of cumulative impact mixing, and why it is important to understand how this process affects the material conversation? Of course, first, it helped the interpretations of returned lunar samples, because lunar samples provide us ground truth reference for a lot of things. If we don't know if if we don't know their origins, and then the interpretations and understanding of other things will become uncertain. Traditionally, people use the samples to infer, to guess what happened in the past. So, but using this model, we are able to think about this question in the other way around. We trace the material conversation since its formation, and then to understand what happened on the present day. It provides us the testable framework of all the things that testable framework to constrain the ideas of lunar bombardment, and also the other things that I showed you today. So today I only shows you these three components that are the three components that we are interested in, and how these components affect and how can we learn from the evolutions of these different components. And of course, there are a lot of things we can simulate caused by this cumulative impact mixing, like impact lock-on and lunar conversational end members, plagioclase, mantle materials, and some, even this model can be applied to the other bodies like Mars. And then, as a very simple example, a very brief example is we can use this impact cratering Monte Carlo impact mixing model to understand the formation of lunar crust. Like here, what we see from the remote sensing, we see obvious difference, asymmetric distribution of plagioclase between the near sides, between the Maria regions and the Highland regions, and also we see obvious difference of the crustal thickness distributions between the near side and the far side. Why it looks like this? So the things we can do now is we can combine the isomodeling results and then use the isomodeling result combined with the Monte Carlo impact mixing model to repeat what we see on the present day. If we can repeat what we see on the present day, then we can say that what happened in the past and then how the lunar crust was evolved with time. Okay, then here, this is my talk here today. So, but at the very end, I would like to take this time to appreciate my my doctor supervisors, Greg Michael, and Kai Uneman, of course, also the Professor Jürgen Oberst. I didn't show you the reference in doing my presentations. If you want to know more in details, you can refer to these publications. Okay, thank you.
Yeah, thank you so much, Tiantian. It was a very interesting talk. I think the the thing you talk about here is mainly coming from your recent paper in 2022, right?
Not only one, because it contains at least for the 3 different components, it has 4 separate publications.
Okay, but I must read your most recent one first. I have a question. I mean, look, anyone from the audience have questions? Please raise your hand or just ask the question. Turn on your mic. I mean, if you even though you find it you don't understand that much, but if you find it interesting, you could still ask Dr. Liu. I have a question to you because you go back to your slide number 32. Is that 30? Oh, I'm sorry, 31. Okay, so this diagram on the left hand side, what is the coordinate?
Coordinate. This is a global map.
So it's a global, right? And then you are talking about the whole surface of the moon.
Yeah, exactly.
All right. Okay. Now, and in your upper right hand diagram. And at 4.3 giga-year, you have this red curve, which has a kink at about 2 kilometers. And that kind of evolved. So that was the original, the initial condition or assumption, or what? I mean, what caused that kink at 2 kilometers?
Okay. This is in this model. I assume at the very beginning. This model assumes the whole lunar crust has not been damaged. It's like a whole target. And then this kink is caused by the formation after the formation of South Pole Aitken Basin. Because South Pole Aitken Basin, it has a very large scale, and then it damages a huge amount of lunar crust and generate a huge amount of fragments with different size. And these fragments, for a lot of regions, it has thickness about 2.5 kilometers. Okay. So this is the kink comes from.
So that's the starting condition, right? Okay, I understand. Yeah. And because I was reading one paper that it doesn't talk about the megaregolith, but talk about regolith formation, and saying that we know that the regolith, the thickness about 5 meters to 10 meters on the size, but it had been there. It had been like that for 3 or 4 billion years. In your megaregolith formation and the thickness of megaregolith, does it stay the same? I mean, only that the fragment kept on being reduced to smaller value, right?
This is a very good question, because in this model, at least for these studies, I only simulate the fragments of with size larger than meter scale, because this is a major contribution for the megaregolith. If I want to understand the growth of regolith, the smaller fragments, I need to do additional simulations. But the big picture is that after the formation of all the basins on the moon, the structure and the spatial distributions of the megaregolith is almost unchanged. And with the time going by, regolith generated, but it only affect and fragmented, shattered the materials of the top few meters. So in other words, the structure of megaregolith is not changed, but the top few meters of these fragments will be further damaged and generate regolith.
This is because the flux of the the impact tides keep on being getting smaller and smaller, so therefore it does not penetrate deeper and deeper. But then in earlier, I mean before, maybe in slide number 20 or 25, something like that, you also mentioned that heating has to do with the thickness of the megaregolith.
Yeah.
Why is that? I mean, the megaregolith is basically just a layer, right, broken down by the impact. But why has that to do with the heating? I mean,
you mean the
thickness.
over the depths over tens of kilometers?
Yeah.
It is because it is mainly related to the first thing. First, why these models here? The result here I only shows you the top tens of kilometers. It is because in the greater depths, the thermal is like thermal softening, because in the greater depths we will have higher temperature, and this temperature will change the properties of fragments. Another important thing to know is that in the greater depths, the pressure will be so big, and then it will compact the materials, and the material will not be fragmented anymore. But at which depths this such kind of process become very significant, it is a study that still need to be to do in the future. Nobody knows.
Okay, good. All right. Any other questions from the audience? Anyone? Raise your hands, or just ask the questions. If not, I think it's 6 o'clock here in Taiwan.
Okay.
Yeah, thank you so much, Dr. Liu. Yeah,
Thank you.
You also, I think I'm very happy and impressed by your work. I mean,
okay, I'm very glad to hear that.
And as you said, keep up the good work. 加油哈，加油。
好的，希望将来可以在线下见到老师。
对对，一定会。Yeah. OK， 谢谢。
拜拜。
再见，拜拜。